Okay, the next slide. Okay, artificial intelligence is a big word that includes very many different aspects. If you have a code, computer science algorithm, or a robotic, or everything that is including the code or the algorithms means in artificial intelligence. But in this big waste field are included the artificial learning. So it means that we can create a network of machine of deep learning according to what are our requests of deep learning, in which we learn the network to learn what we want that it learns according to our target that will show later. So machine learning and deep learning are the same structure, but deep are deep. So it means that we want to learn more particular characteristics or extract particular features from a particular input. Okay, go on. It inspired by by our brain. So, like how our brain learn from the external input. We have contact with the world outside ourselves according to our five senses, so visual, hearing, and so on. This is the way in which we take the input from the outside. Later, from through a network of connected neurons, the information passes step by step inside the brain regions of our brain. And this connected neuron it what we decline like learning. So according to this, if you go on with the slide, according to here, we will create a network of layer in which step by step, layer by layer, we can transform an input in an information. Information that obviously can be many different kind, visual, sound, and so on. This deep neural network consists just of a hierarchy of layers. From a mathematical point of view, this means that each layer is a function or a set of functions according to what we want to learn and extract but from the input. Go home. Okay. Obviously, we said about machine of deep because from our brain, so in the same way from a network, can be easily distinguished from, for example, a table or a tree, or for example, a human or on a car. But when we want to, for example, distinguish from two similar forms, similar shape, for example, a cat or a dog, we need more information. So not only that animals are not only for harms or eggs, bags, and so on, but we need more information. This traduces it more layers of information to extract deep and deep features from the input. Go on. Okay. We want in this slide you can see a typical neuron of our brain, our system, human system, in which you see that a neuron receives the inputs according to biological system, transforms the inputs in outputs, and these outputs will become the inputs of the next layer, and so on. In a mathematical way, like we introduce it, we have the x is xj is our inputs. The w way is weight, and this weight is what the network at the end of the training process will optimize to understand what are the characteristics that the network have to take from the input. These arguments, input according to weight are linked to the neurons points according to our goals, are connected and passed like an argument to a function, phi in this case. This is activation function. Activation functions is fundamental to describe, to extract characteristics from the inputs according to our targets, and we'll see how. Go on. Okay. This, for example, is a classical and simpler architecture of a neural network. This is a feed-forward neural network. So it means that from the left to the right, there is only one direction forward. But it's a simpler architecture. It's not only architecture, because we see that we can have also nested architectures or in a way forward and backward. In this, we have a multi-layer, we can see multi-layer perceptron. What it means that we have, for each layer, different neurons. The little circle is neuron in this case. Each neurons represents a weight different with a different filter to filter the characteristic. So you can see from a mathematical formula in the bottom on the right that the first argument will be worked in the neuron in the first layer. It will become the output, and this output will become the input of the next layer, and so and so and so on, since to the end in which we will have our output. Okay, go on. Okay, for example, if we have an image like input, because we have input of every kind, so image, sound, linear, time sequence, vector, like you want, from a real point of view or mathematical point of view, is the same. From a mathematical point of view, an image is composed by 3 different matrices, okay? Red, green, and blue. So if we, for example, on the right, construct a structure on a neural network in which we have this different layer, image input layer, convolution 2D layer, radio layer, and so on, since to the end, classification layer. What it means, for example, we have our image, a car. So we have 3 metrics for identify this image. This is only one input. We applied in the second layer, convolution layer, a convolutional matrix, you see 1001, that will extract a particular characteristic. In this case, for example, the age of the image. So with a mathematical process, we do a convolution from a matrix of image and this filter, and obtain a different matrix, and so on, layer by layer, radio layer, max input layer, are connected to a particular function, since to arrive to the end in which we have a probabilistic, in this case, response. So, well, when we have measured the principal probabilistics, will be the class in which we classify our input. Go on, please. Okay, so this can be applied to everything. For example, if we have an input image, we can have a filter that recognizes some particular part of the image. With another filter, we can apply the second particular, the third particular, and so on. Things too, we understand or capture different characteristics of features of our input. And this can be applied in everything, nature, biologic, flowers, because we can interpret it through an interpretation of the matrix that describes our inputs. Go on. Okay, and what this means? we can, from a feature, for example, or a general input, we can have different information inside the figure. So we can, for example, in this kind of figure, recognize animal or plant, object, and so on. So the first problem of the neural network processing is that the quantity of data. So we call augmentation data, the process in which we have to have not only a single input, like I said, like for example, a dog, a picture of a dog, but this picture that have to be augmented. So we have we have to have this figure in different form: original, colored, rotation, flipping, and so on. Because when the network will finish, the network have to be able to recognize the object in every shape it will find it. Okay, this is the first big problem of the neural network, because we have to elaborate many a very wide quantity of data, thousands and thousands or million or so of data. For example, the big trained network like Google Net, ResNet, SqueezeNet, and so on, have a data of millions of pictures. Okay, and this means also many time to train the network. Go on. Okay, but when we have our network, our training network, we can apply it to what we want. So biological, flowers, leaves, geometrical forms, like you want. Not only in 2D, but also in 1D imaging. In fact, go on. For example, a part of this process is, for example, the analysis of sound, of the music, of the language, and so on. You can see an audio data like a signal, for example, or like an image. So you can pre-process the data according to some rules, extract features in 1D or 2D, for example, a spectrogram and the frequency domain, and so on. Applied your network, in this case is convolutional recurrent network, to have your goals. In the moment, for example, I won a contract with the Conservatory of L'Aquila, in which we want to apply these techniques, so our neural network architectures, to map a creative of a compositor, in particular Rossini. So according to the study of his writer of the partiture, we would like to reconstruct this ambitious goal. So the object in which you can apply the neural networks is very, very vast. Go on. Okay, now deep inside, just a few to the structure of a neural network. Machine and deep learning are similar, we said. They are four major macro area, and divided in supervised and unsupervised. Supervised means that we know the label of the input. So now we know the input. For example, we have an image of a dog, and we know that is a dog. Unsupervised, instead, we have a data, but we don't know still the label of the data, the kind of the data. So according to this, we can obtain different targets. In supervised, especially used for predictive, so like, for example, classification of data or regression of our data, forecasting, for example. Unsupervised, instead, used for clustering, so create group according to similar characteristic of the data that we still don't know, or individuate anomaly detection. So for example, we have a signals and we wanted to identify an anomaly at outlines during these signals. Like you see in black, FNN, CNN, RNS, and so on, are only just a few particular architecture that we can use for these targets. Like you see, they can be transversal to different targets, because There are many steps of process in create neural network architectures. One step is create a sequence or layer, but another step is create a particular function inside of a particular neuron inside the layer. This means a different function. So the same architecture can be used for different targets by changing only some activation function for the targets or for what we want to obtain. Go on. Okay. Okay, there are, when you train a network, you can set many different, what we call hyperparameters. These hyperparameters, sorry, maybe there is someone with the microphone open. If you can get off, please. Okay. One of the
evaluation.
One of the principal aspects that we have to consider is the activation function, like we said. There are many different activation functions. This shown here is only part of this possible choice. And obviously, according to what we want to obtain. I mean, if I want to obtain a classification, I need to construct the probability from 0 to 1 or from minus to from limits, no, minus limits or plus limits. So I can use, for example, function like a logistic, hyperbolic tangent, and so on. I cannot use a linear function for classification because it's not limited from, for example, 0, 1. But I can use a linear activation function if I want instead obtain a forecasting, for example, forecasting of some profiles or what we want. Okay, in this case, I can use, for example, the Adaline or linear regression for this target, a linear function. At the end, we'll obtain the output always through a bias theorem, so the probability theorem and results. Go on. I'm sorry that you cannot see the animation on this slide. I'm very sorry. Oh, anyway. Okay, another point, because this animate this. Okay, another point that we can put attention is the optimization process. What it means. When we finish the train of this network, we'll obtain output. In supervised, for example, behavior environment, at the end, like how we can know if the network learned well, okay? By a comparison from the output predicted, created, and the output through that we passed in supervised mode at the beginning of the process. At the end, we'll have to compare an error function. We create an error function to compare these two results. And we have to analyze the minimum of this error function. There are different techniques to analyze this minimum. One of the most common used is involving the gradient method, in particular the descent gradient method, because we will find the minimum local math. We are interested in global minimum of this function. Go on. Okay, this descent gradient method is iterative method. We have to start with the choice of initial learning rate, this parameter that will involve our gradient, and step by step we'll optimize this error function. The choice of this initial learner rate is another key point, because if we choose a learning rate much too high, we can have a divergence. So we cannot find the minimum never. In the opposite, if the learning rate is too low, the process is very slow. So we can arrive to the minimum, but with many time. So the object is find the equilibrium in this choice of these hyperparameters. And you do this through a simulation and step by step. Go on. Okay, you can, I'm sorry you cannot see the animation of this slide because you can see these different methods, the gradient descent, momentum, adagrad, and so on, are represented for this little ball that go to this minimum, local or global. So you can, is a sympathetic way to see like different methods can reach the goal in more or less time or cannot reach the goal. Okay, I'm sorry. Go on. There are another problem that we can face with the implementation of a neural network. They are under or overfitting, because underfitting means that the network create an approximation of our data, optimize the weights in not so good way. So what it means that many information of our data set will be not included in our response. So when will use our network training network for our goals, maybe many inputs will not recognize. On the other hand, overfitting will mean exact opposite. It means that is not created an approximation but interpolation. So the network will learn precisely the characteristic of the data, but it will be too much linked to this data, and it will not able to generalize the concept. So when I will use the network to recognize, for example, another input slightly different from the data set that I used for training the network maybe will not work. Go on. Okay. Now deep in this 5 minutes, we go deep inside to my simulation according to my project. The different, I use in my current simulation a recurrent neural network. What it means? We said that the first simpler neural networks is the feed-forward neural networks, in which we have an inputs and the arguments passed to our activation function, like we said before. But if we go on, in time sequence, so in a recurrent philosophy of a neural network, you can see in the time sequence that we have an input, okay, but when we create an output, you see inside the H, that is our output, we have the XMK. It means the input at the time K, but the output of the previous time, HK minus 1. It means that this kind of network is capable to link the information of the present and of the past. So it is the record, this is called the recurrent neural network, and this is very useful to capture dependencies in the sequence. For example, in this case, we have not an image, but a vector, but it's the same in 2D. And we can capture the sequences. So, for example, if there are some information that are repeated during the time. This can be useful for electrical signals, sound signal, language, and so on, for example. In particular, I use the particular recurrent neural network called long short-term memory, because it is capable to capture as long-term dependency. And we can combine also different architectures, for example, long short-term memory and convolutional for the image, and applied it to 2D and so on. Go on. Okay, so if we, for example, have a simple convolutional structure, you can see layer by layer, function by function. We include in this process a long short-term memory. Long short-term memory, by mathematical point of view, is did like you see, because there are this gate for gate, input gate, and so on, in which every gate, every cell, at the characteristic to, for example, fix or delete or move some information according to what we want. And this kind of mathematical architecture, if you go on, can be included inside the convolutional. In fact, if you see the system in the in the high part of the slide, you can see that we combine LSTM with a convolutional mathematical process. And this means that we can put together different architecture. CNN, LSTM, COMB, LSTM are two architectures, always the two architectures, but combined in different way. We can, for example, in the CNN, LSTM, we start with convolution and later applied long recurrent neural network, or in COMB, LSTM, we can combine these different mathematical functions and steps. Go on. This only to give some idea of the strong of these architectures. These are a typical structure of the what we call PIN, physical informed neural networks. They are very strong because they are used for problems involving ODE, OPDE, and physical problems. So they can incorporate equation into models. So physical laws, for example, mass of energy conservation, physical laws relevant to the problem, so on. Experimental data too. So the experimental data can be incorporated into the training together with the physical law, allowing the neural network to learn from both physical laws and real data in real time. So when while the network training this iteration, it can be learned from the experimental data, including step by step in this process. This has a flexible structure, fully connected layers or convolutional layers depending on the specific problems. It is very important that it can be used as for inverse problem. I mean, if we haven't initial or boundary condition, but we have experimental data, from experimental data, we can go backward to this initial condition. And this can be applied to very different fields of research. Go on. In my particular context, in energy context, I apply this long short-term memory and similar structure to real-time monitoring of smart grids, so signal recognition, fault detection, data transmission from multi-energy vector. In energy production forecasting, so for renewable sources, demand response profile, multi-energy vector, and so on. But these are only just two simple examples of how we can imply the neural networks. Go on. For example, I create my architecture. I tested it on periodic signals that I created to can control the results, because I know these signals. The signals are periodic or similar periodic, like for example, sin to 4, Bessel of order 2, logarithm for sin, and so on. And what I did, I created 6 different groups of functions, but for each function, I create 1,000 and 1,000 of function with white noise, with the Gaussian distribution. And this family of original signal and noise, and signal with noise, have the same level. For example, since to 4. And this is the process to train the network. I need many thousand of information. Go on. At this point, when I set the hyperparameters, function, layers, dataset, and so on, I can train it with the simulation, step by step. Like we see in the first picture, in the up of the slide is the accuracy function. So we want to reach the maximum of this accuracy. In the function below, you can see the loss function. So we want that the loss function reach the 0 or similar to 0. What we see in the second graphics is the confusion matrix. What it means that in the diagonal of this matrix, it means that the predicted class in horizontal axis are corresponded to the true class in the vertical classes. So if we have results in the diagonals, it means that the network is perfect. And I obtained this by setting step by step, simulation by simulation, time by time, the parameters. These are only some summarize of the parameters that I set. And I, step by step, for example, I passed from accuracy of 96%, but with 236 minutes of training time, to 99% of accuracies, but with only 55 minutes of time training. And this is important, no? Because it's important to reduce the time training. Okay, at this point, the network is trained, it is flexible. I know that it is works, and I can apply it to our goal, our context, our experimental data. In fact, I applied it, if we go on, I applied it with my colleagues to, we chose, this is the photo of the campus of University of Palermo. We selected some buildings, and these buildings, we set some characteristics, like, for example, external temperature or internal temperature, meteor condition, number of occupants, number of devices, electrical devices, and so on. And my colleagues with a particular software obtain some profiles. This you can find in blue and red, are two profiles of electrical request, so power request, in 1 year with a step of 3 minutes. So I applied it to this kind of profiles. If you go on. Okay, I divided, for example, in 12 months, or in 1 week, or in 1 day, and so on. I applied my trained network, and I obtained very good results in terms of accuracy. And what it means that we can, through our network, recognize, for example, what kind of profiles we are analyzing, what months, what weeks, what period, and so on. But this is only just a sample of what we want. This is applied energy context for classification, but we are working, for example, of forecasting. So if we have the same condition of the building, I have, with this process, obtained the same forecast of the energy context. And that's all. This is only a general overview of the world of neural network. We can conclude. I finished this short list of publication. We go on the acknowledgement. And the last slide to conclude that we can work many with different mathematical artificial intelligence, but we have always to consider that, if you go on, that God said, "Let there be light," and there was light. But the electric company said it should wait until Tuesday for the connection.
Thank you.